next topic is fluid statics. And fluid statics being, we're mostly going to talk about water, and statics being the fluid is not moving. So in other words, the fluid is stationary, which contrasts with what you will learn in a future class, which is fluid mechanics, where you'll be talking about flow of water through pipes, for instance. So right now we're just talking about, in this particular case, we're talking about fluid in a container, and in this particular situation we are interested in, for instance, finding what are the forces on this wall. So we know that water exerts a pressure, and we want to know what will be the force exerted on this wall. We know it's going to be a horizontal force on this wall, and we want to know what its magnitude is. There are two rules that we follow, and they involve basically determining the magnitude and the direction of the water pressure. So the magnitude is the depth times the weight density of the fluid. And like I say, we'll mostly be talking about water here. So that gives us the magnitude. So you need to know these rules, okay? So know these rules. They're pretty straightforward. So the magnitude is the depth times the weight density of the fluid, and the direction is perpendicular compression toward the body. In other words, like we've always been talking about, compression is toward the body to the surface of cut made through the fluid. So in other words, we are going to make cuts through this fluid, and we will look at free body diagrams, and we have to make sure that when the direction that we put for the pressure, we have to make sure it's perpendicular to that surface. So in other words, if I make a cut through the fluid like that, well, it's going to be perpendicular to that. And it's going to be toward it, toward that surface. So that is the meaning of this second rule. And again, the first one, the magnitude, is the depth times the weight density. So if D is the depth and gamma is the weight density, then P is the pressure. It's that simple. It's D times gamma. Now for water, what I want you to memorize is that water is 62.4 pounds per cubic foot. That is the weight density, or 9.8 kilonewtons per cubic meter. So you need to memorize this. So we'll just say memorize these two numbers. And like I say, you'll need to memorize those for the rest of your life, because no matter, what you become involved with, you're going to be dealing with water in your profession of civil engineering or mechanical engineering. Okay, so what are the pressure units? Well, that we're going to be working with are pounds per square foot, PSF, pounds per square inch, PSI, kilonewtons per square meter, which are kilopascals. Newtons per square meter are pascals. And we should note that pressure is not force. When we do our free body diagrams and we work with our equations of statics, we need to use force to analyze our free body diagrams. So we must convert pressure to force. So we're going to be spending time doing that. We're going to get some pressures, then we're going to convert those pressures to forces. And this symbol here, that is indicates our water surface. So we're going to use this symbol. It's a triangle with a couple lines underneath it. That means that is our water surface at the tip of that triangle, the bottom tip of that triangle. Okay, so here's our first example. And what I want to do is find the reactions at points A and B. And we're going to use 1 foot perpendicular to the paper. So we need to have a dimension of our container here. And I want you to use it as being 1 foot perpendicular to the paper. Now we have this wall, and it is pinned here, and there is a roller there, so that's A and B. And what we're going to do to determine the reactions is, first I'm going to figure out what is the pressure exerted by the water onto the wall. So I'm going to come in, I'm going to make a cut. Now I'm going to make a cut at the roller, at the pin, and then I'm going to cut through the water right next to the wall. So I'm going to cut close to the wall, but I'm going to cut a hair into the water. So I'm making a cut through the water here. So this is a cut through the water. And that means I have to follow the rules for making a cut through water, which is the pressure rules that I just showed. Remember, when we make a cut, as we said, we make a cut through a pin, what do we put? An X and a Y force. I make a cut through a roller, what do I put? Well, I put 1 perpendicular, whether it's X or Y, but I put 1 force perpendicular to the roller. And when I make a cut through water, what do I put? I put pressure. And what do I know? If the pressure is d gamma w, depth times the unit weight of water, the density of water, then at the bottom, well, how deep am I? Well, I'm 10 feet deep at the bottom. So down here, I'm at a depth of 10 feet, so d is 10 feet. The density of water is 62.4 pounds per cubic foot. And so I multiply that out, I cancel the feet in the units, and I get 624 PSF, pounds per square foot. At the surface, the depth is 0, which is going to tell me that the pressure is 0. So I know the pressure is 0 at the top. It's 624 at the bottom. So I have 0 at the top. I have 624 PSF at the bottom. Now, we're using 1 foot perpendicular to the paper. So in 3 dimensions, this is going to look like this. It's going to look like a wedge of cheese, in a sense. So you need to visualize that, where the thickness of the cheese, thickness of the wedge, is 1 foot, because I said to use 1 foot perpendicular to the paper. And so we want to get the volume of this, the volume of that is going to give us the total force. And how do I get the volume of that? Well, the volume of that wedge is 1/2 the base times the height for this triangle times the thickness. There's my thickness, which is 1 foot. So I'm going to be true to my units and what I've written here. So I have 1/2, and then the base. Well, the base, and I can use as 10 feet. 10 feet for B. Then the H is 624 pounds per square foot. And then the thickness, T, is 1 foot. And if I look at this, I'll see that the units cancel out, so I get that feet and that feet canceling with that, and then I end up with only pounds. I multiply it out, I get 3,120 pounds, which is the force. So I've converted my pressure to a force. And just like we did before, where does it act? Well, it acts, we use the 1/3, 2/3 rule because this is a triangle, and so I'm going to take 1/3 from the bottom then, because that's the fat end of the triangle. We've done this, and it's 3.33 feet. So I have that, and then once I've established this, well, we've done this a million times, so we take the sum of the moments about A equals 0. You can read that. We get BX. Sum of the moments about B equals 0. We get that. We calculate out AX. And the sum of the force in the y direction tells us that AY is 0. So my final free body diagram looks like that. And we've solved the problem. So this is a homework problem for you. Let's take a look at this. Again, I have a wall here, and I have it pinned at B, roller at A. Very similar to what we just did, except now the tank is, I can go higher than the wall here. So it goes up higher. So that's one difference. The other thing is the tank is 15 feet perpendicular to the paper, so I want you to take 15 feet. And we're going to find the reactions and draw the final free body diagram for the wall. Now, notice where the water level is. It's up there. And previously we just, the water pressure level, or the water level, was within our wall. Now it's up above the wall. So in other words, the water pressure here is the water level here is up above the wall. Now, I've given you this distance 8 feet. It ends up this distance 8 feet has no impact. You're not going to use this at all in this analysis. It ends up that, using our method, it doesn't matter what footage that is. In other words, I could have this situation here, and it could be very narrow here. So that this may be, an inch or 1/10 of a foot, just to keep the units the same, 1/10 of a foot. It's not going to impact this 8 has no impact. This could be 1,000 feet, or it could be, 1,000th of a foot. How about that? It doesn't matter. That's the way water pressure works. It's just we have to follow the rules which we laid out. So don't get confused. It has nothing to do, the pressure on this wall has nothing to do with the volume of this container. It has nothing to do with the volume of the container. When I talk about volume, remember I want the so-called volume of the pressure diagram, not the volume of the container. So don't compute the volume of the container. Volume of the container has nothing to do with anything. And in this problem, you can see I didn't give you you can't compute the volume of the container here. I did not give you this dimension, and it didn't affect our problem. So one thing that I noticed students, once we start talking about volumes, they start wanting to figure out the volume of the water. Do not figure out the volume of the water. The only thing, we've got our two rules. We have to follow our two rules, which are simply that the magnitude is the depth times the density, and the direction is perpendicular compression. So notice volume does not play a role. Volume of the fluid does not come into this at all. Has nothing to do with what we're solving here. So be aware of that. Okay. So pause the video and do your best to solve this problem here. Okay, if we follow our rules, so I'm taking a free body diagram of this, and notice I cut through the water again, and I cut through the roller and the pin. So at the roller I've got one force, at the pin I've got the two forces. Now I need to figure out since I'm making a cut through the water, I have to figure out what the water pressure is. So I'm just going to figure it out at the top and the bottom. It's linear in between. I guess I didn't mention that. It's linear. The water pressure increases linearly. You can put the equations on that to see that. But what do I see? Well, I find that I have to figure out the water pressure there and the water pressure there. And the water pressure here, what's the depth? I have to, well, the depth is actually 5 feet. Because I am 5 feet below the water level. It doesn't matter that I'm inside here. That doesn't have any play on it. And so I just see that I'm down 5 feet. So my pressure is going to be 5 times 62.4, which is 312 psf. Down at the bottom, well, I'm 13 feet down. So it's going to be 13 times 62.4, 811 psf. So I have 312 here, and I've got 811 there. And then what do? I connect them with a straight line, and I end up with a trapezoid now. And we've dealt with trapezoids before. What do? We break them into rectangles and triangles. So we're going back to that in a sense. And I didn't draw this one in 3 dimensions, but it's similar to the other one in that it's a wedge. I mean, I guess I could, draw it somewhat here. It's going to look like that. And what we need to do is we need to find the area of the both the triangle and the rectangle. So I've got one that's a rectangle and the other that's a triangle. Looks something like that. And so I've got So I find the area of this, which is 312 times the length of the height of the wall, which is 8. So 312 times 8. And then what? It's 15 feet perpendicular to the paper. That's where that comes from. So that is the volume of this wedge here, well, of this. And like I say, if I drew it in 3 dimensions, it would look something that looks like that. And then if I need to get the volume of the triangle portion. So again, it's going to be 1/2. Whoops. It's going to be 1/2 the base times the height. So I have the base, I'm using this as the base, the 8 feet. So it's 1/2 8. And this works out to be 499. You can see we've done the trapezoids before, so you know how to do that. So that gives me the area of this triangle, and then I take 15 feet perpendicular to the paper, which we said before. This distance is 15 feet. So I get the volume of the triangular wedge and the rectangular wedge. So there they are. There's the 2 volumes, which means that these, if we look at we can do the units, we'll find that that is a pound, that is a pound, for the same reasons that we had before. And we put them in the place where they belong, which is 1/3 from the bottom for the triangular portion, 1/2 from the bottom for the rectangular portion. So for the rectangular portion, this is 4 feet from the bottom, and for the triangular portion, it's 1/3 of 8, which is 2.67. Once I have all these dimensions, now I have my free body diagram. I can simply take the sum of the moments about A equals 0, sum of the moments about B equals 0. You can all do this. I'm going to leave you to pause the video and look at those numbers, and then I can solve for Bx, I can solve for Ax. By is 0 again, because there's nothing going on in the y direction. And the end result is I have this final free body diagram. Putting these numbers here, like that. Now we're looking at this right here. That wall, again, I have a pin and a roller, and the tank is 6 feet perpendicular to the paper. So follow the rules and find the reactions at A and B, draw the final free body diagram. So pause the video now and do this problem. Okay, this one ends up to be pretty simple. Again, I'm taking this free body diagram where I cut through the water right next to the wall at the roller and at the hinge. And when I do that, what do I see? Well, now I get this. And how do I get it? Well, I need to figure out what is the depth here. Well, the depth here is 8. The water level is up here, so I have to go all the way up to the water. Okay, in other words, it's not 0. It's not 0 because I have to use the water level here. And that water level is 8 feet above that wall. And in this case, both points here are the same depth, the 8 feet. So I take my 8 feet times gamma W, 8 times 62.4 gives me 499.2 pounds per square foot at both of them. So I have 499.2 pounds per square foot. Gives me a rectangle. It's 6 feet perpendicular to the paper, so I need to get the volume of this. If I, you know, like I say, it's going to look like this, where this distance is given to be 6 feet. And this is 7 feet, and that is 499.2. So to get the volume of that, we have 7 feet times 6 feet times the 499.2, and the end result is 20,970 pounds. Okay, so oops. Where does this act? Well, it's a rectangle. So that means it acts at the center. And once I have that, then I can take the sum of the moments about the 2 points, and I can get the forces. Everything's symmetric, so the easiest way to, well, this one you can do in your head, recognizing that everything's symmetric. This is dead center, and so that means that, and these are at the ends, and that means that, you know, this force is half of that force. Okay. This is, we're going to use 1 foot perpendicular to the paper, find the reactions at A, and the question is, will the gate rotate clockwise? Okay, so this is an unusual situation. It's different from ours that we've looked at so far, in that, yes, things are static, but you can see the way this wall is, it's only supported at one point, at the pin. So that means that the wall is going to rotate. It's either going to rotate in this direction, or it's going to rotate in this direction. We don't really know. But in this particular case, we want to know if the gate will rotate clockwise. So clockwise would be like that. So will the gate rotate like that? So a little bit different. You know, the way that we look at these things is there's still going to be, some of the forces are still going to be zero. But anyway, I want you to think about this problem and work this one and try to do your best and answer this question. Now you need to get the reactions at A, so that means you've got to be able to get the pressures and everything like that. So pause the video here and do your best with this problem. Okay, so, you know, in some ways it's very similar to the very first problem we did. I have 0 at the top, I have 12 times gamma W at the bottom, which is 12 times 62.4, 748. And again, I have a triangle here, which means I have to use 1/2 the base times the height. It says use 1 foot perpendicular to the paper, so it's 1/2 the base times the height times 1. And that means that we put in our our B in this case will take us 748. The H, there's my H right there. The H is 12. And then we're taking 1 foot perpendicular to the paper. So we end up with F is equal to 4488 pounds. Now where is it? It's going to be right here. Well, what does that mean? That means that this gate is going to rotate in this direction, which is clockwise, or sorry, counterclockwise. And so it's not going clockwise, it's going counterclockwise. It rotates counterclockwise. Now, so how do I know that? Because I'm taking moments about this point. Now notice, this is our first free body diagram where the sum of the moments about A do not equal 0. So we're getting into the next step that eventually is going to take you to dynamics. We're going to look at a couple problems where, you know, I didn't ask for final, I didn't ask for, you know, a final free body diagram, and this isn't the best problem in the world because of that, but you can see that this clearly is not in equilibrium, and so it gives us, but it still gives us a clue as to what would happen. Now, so what we would see is, if I'm since we're concerned about the only way that this gate is going to rotate is about point A, so it will rotate in this manner. So it would rotate counterclockwise, and not will the gate rotate counterclockwise? Will the gate rotate clockwise? The answer is no. Okay, here's another one. Now the gate is tilted a little bit. Well, how does that change things? So again, it's 5 feet perpendicular to the paper, so we're taking another dimension there. And I want you to draw the final free body diagram of the gate. Now in this case, again, we have a hinge and a roller, so it's different than the previous one. So this one will be in equilibrium. And it says to follow the rules. Of course, we've got to follow the rules of pressure, which are the 2 rules, which is the pressure magnitude is depth times the unit weight of the fluid, the density of the fluid, and the direction is perpendicular to our surface. So we're going to be taking a cut, again, like this, where we cut the hinge here, we cut the roller here, and we cut the water right next to the wall. So now what I want you to do to make this problem simple is I want you to first draw the pressure diagram on the gate. So do that first. Draw the pressure diagram on the gate. And then rotate the drawing, rotate the gate drawing so that it looks like our beam problem. Okay, so in other words, I've posted here what you can use for the XY axes, but we want to rotate it in such a way that the XY axes are that. So that's the easiest way to solve this problem. So in other words, I want, you know, you're going to take this and you're basically going to flip it like that. So that it looks like our beam problem. So that's what I want you to do. And follow the rules, which means I want you to fill out this table and fill out this table right here. And I filled out part of it for you, point A, point B. Well, point A is what? Is it at a depth of 6 feet? It's at 6 feet. Point B is here. It's at a depth of 2 feet. So then you fill out the pressure. So if I look at this, point A is at 6 feet, B is at 2 feet. Well, that's pretty straightforward then. It's 6 times 62.4 at point A. It's 2 times 62.4 at point B. And that's these numbers here. So I have 124.8 at B. I have 374 at A. And that means that I have a trapezoid again. And so I have 124.8 here, 374 here. I connect them with a straight line. I end up with this trapezoid. And I rotate it. So I rotate this to get it to look like that. And now it's in our, we've seen this before. Looks like our beam problem. We just have to take the 5 feet perpendicular to the paper. And so if I draw this in 3 dimensions, I get that, where this distance is 5 feet. And what do I know? The volume of this gives me the total force. And how do I get the volume? Well, I'm going to get the volume. I'm going to get the volume of the rectangle, volume of the triangle. It's the easiest way. You can all do this, so please take a look at it. Well, it's for the rectangle, it's that times 5 feet perpendicular to the paper. That times the 5 feet perpendicular to the paper. That gives me the volume of the rectangle. The triangle is 1/2 the base times the height. 1/2 the base is 5.66. And the height is 249, which is what? 374 minus 124.8 equals 249.2. So that gives me the volume of the triangle portion. So I then I just do what we normally do, which is I got the triangle, 3523. It goes 1/3 of the total distance. And then I have the rectangle, 3538. And it's a dead center. And so that dimension, well, is 2.83 from the left end. And then once I have this diagram, I can take the sum of the moments about A equals 0. I can take the sum of the moments about B equals 0. You can all do this. I get my reactions at A and B. Okay, one more gate problem, and that is what depth of water, H, will cause this gate to open by rotating clockwise about point B. In other words, if I look at this, here's my gate, and I've got a pin here, I've got a roller there. Well, this gate cannot rotate like this. So, which is counterclockwise. It can only rotate clockwise. It can go like that so that the wall looks something like that. It's going to rotate. So the question is, at what depth of water H will it rotate? Well, we got to find the pressures here. So why don't you, okay, you work this one. Pause the video, work it through. Okay, well, this total distance is H. I know this is 3, that's 5. So, and this is given as H minus 8. So we have all the depths here. I want to know what's the pressure here, what's the pressure here. Well, the pressure at the top is going to be H minus 8 times gamma W. The pressure at the bottom is going to be H gamma W. And so I get a trapezoid that looks like this one. And I can break it up again into rectangle and a triangle. So it's the same sort of thing in a sense. And the triangle is going to be one half the base times the height. And the other one is base times height. And we know that, so in other words, we know that this pressure is H minus 8 times gamma W. So that means that the distance, well, we know that this distance here is 8. So the volume, because I didn't draw it in 3 dimensions. If I were going to draw this in 3 dimensions, oops. If I were going to draw it in 3 dimensions, I would end up with that third dimension. And what we're going to do is we're going to take, since there's nothing specified, the way to do this is to just take 1 foot. It doesn't really matter how deep this is into the piece of paper. That's not going to affect the problem. So we're just going to take 1 foot to get the volume. So it's going to be H minus 8 gamma W times the 8 feet times 1. That gives us the volume of the rectangle, and then, so that's, 8 times H minus 8 times gamma W, and then this one's going to be 1/2, oops, this one is going to be 1/2 the base times the height, so it's going to be 1/2, and this portion is 8 gamma W, and so it's, and then of course this is still going to be 8, so it's going to be 1/2 times 8 gamma W for that one, and it goes up 1/3, so it's 2.67. This one goes up 1/2, which is 4. The BX is at 3. So so I can take my moments. My clockwise moment is going to be this. Again, we're at the situation that we're not having equilibrium here because this gate is about to rotate. And so now notice one other comment is that, and maybe I skipped this here. Okay, I guess I didn't say this, but it's important. When this gate starts to rotate, just as it just starts to rotate here, what happens? It separates from that roller. So this particular roller actually is the way that I've drawn it, so this little sketch is meant to represent a roller in that manner, because this is going to be free to rotate. So in other words, it lifts off from that roller. In our other problems, I wouldn't let it lift off from the roller, but this one we will. And so once it begins to lift off, there's no contact there. If there's no contact, then there's no reaction there. And that's why I did not show no reaction. No reaction because the wall begins to rotate. That's the assumption. That's what we want to, so we don't have a reaction there. And so what we're interested in is we want the clockwise moment to be slightly greater than the counterclockwise moment. You can see that there's a moment going around this way, but there's also a moment going about this way. And so when the clockwise moment is just slightly bigger than the counterclockwise moment, then we know that this gate is going to rotate. And so I'm going to set them equal to each other. That's when it just starts to rotate in a clockwise direction. So I set this clockwise moment equal to that clockwise moment, or counterclockwise moment, and then I simply solve for h. It's our only unknown here, and h is 9.33 feet. Okay, I'm going to stop here.